Hi, I'm April and welcome to the channel. I teach standard level IB math. In this video, we're going to be looking at some simple deductive proofs. In the first two examples, we'll look at some proofs where the variables are already defined, and we will examine a common pitfall that students tend to fall into when structuring their proof. Then in the last example, we'll look at a proof from start to finish where the variables have not been defined, and we'll take a look at how we can properly structure our proof for a full, complete solution. Let's get started.
Consider any three consecutive integers, n minus 1, n, and n plus 1. My first line is taking the sum of these three integers. We simplify and we notice that we have 3n, which is always divisible by 3. This is a very simple deductive proof. The examiner is looking for the sum of these three integers and stated result. Now let's take a look at another question. The next question says, prove that the sum of the squares of these three integers is never divisible by 3. So I'm taking the square of each of these three integers and I'm summing them together. We expand each of these expressions and then we simplify. So we collect like terms. All the n squared terms, we notice that the n terms cancel out and the constants add up to give 2. Now at this stage, you can either explain in words or show an algebraic proof. We know 3n squared is divisible by 3, which means that 3n squared plus 2 is not divisible by 3. It's important to give a reasoning here. And then, of course, we have our concluding sentence. The sum of the squares of the three consecutive integers is never divisible by 3. What are we looking for here? There needs to be some attempt to expand either n minus 1 squared or n plus 1 squared. There has to be a correct expansion of those binomials. There's a second accuracy point for your final answer, a reasoning point for stating why 3n squared plus 2 is not divisible by 3. You need to state a final concluding answer in order to tidy up and clean up your proof. Here's a word of warning. By setting up their expression correctly, they're taking the sum of the squares. But then in the next couple lines, look what they do. They are breaking up their proof. This shows a lack of continuity because instead of continuing from one line to the next in a very fluid and easy to understand way, they're taking individual terms from the original expression and isolating them as a part of their proof. This is not a very good way to show your understanding. Do not do this. Rather than having your proof being broken up into segmented parts, continue with one line leading logically to the next line. If you need to do some work on the side, do that on another piece of paper, but do not have it as a part of your formal proof. Notice the difference between this proof here, where each line is equivalent to the one before it, versus this solution where the first line does not match with the second and the third lines. Prove that the sum of the squares of any two consecutive odd integers is even. We must start by defining our variables. Let 2n plus 1 and 2n plus 3 be the two consecutive odd integers. Since when I plug in any value for n into these expressions, I'm always going to get back an odd number. Please note that 2n plus 2 is not the next consecutive odd integer. If I had 2n plus 2, that would actually give me an even number. Okay, so in order to get to the next integer, I have to add 2. From here, we can set up the first line of our proof. We're taking the sum of the squares of these integers. In the next line, we can expand each of these binomial expressions. We combine their like terms. And then in order to prove that the result is even, we must be able to factor out a 2. And you can summarize this as 2k, where k is an integer. So whenever we have something written in the form of 2 times some integer, I know that that whole expression is going to be even because even numbers are always divisible by 2. For a question like this, there would be a method mark for attempting to set up your variables, an accuracy point for correctly defining those variables, another accuracy point for setting up your expression, to expand that expression, and then an accuracy point at the end for a correct result, demonstrating that whatever expression you end up with is even. And of course, you have to state a concluding sentence at the